Okay, so welcome back. Our next speaker is Mark Spradlin, and he'll be telling us about scattering amplitudes, positive geometry, and the Amplituhedron.
Okay, yes, thank you. Thank you for organizing this wonderful workshop. It's a great idea. In fact, I think you should make it annual. So yeah, so I'm going to be talking about a few related topics that just describe various aspects of the interplay between the math and the physics that we encounter in n=4 Yang-Mills theory. This is a fantastic topic for mathematicians and physicists to talk to each other about. I sometimes describe the scattering amplitudes of n=4 Yang-Mills theory as if we're discovering some ancient scrolls that have been hidden for thousands of years in some obscure cave somewhere, and we're just trying to decipher these really remarkable functions and understand their properties. And you know, they're also physically relevant, which is exciting. It's not just some completely obscure made-up quantum field theory. It's all very highly relevant to physics. But anyway, so the brief outline of my talk, I'll give a lightning review, then I'll give a status update focused on n greater than 7, as Anastasia said, advertised that I would. And then I'll say a little bit about Yang invariance, cluster adjacency, and finally, in response to one of the questions that she had at the end of her talk, I'll try to make some connection to the loop amplituhedron. Okay, so lightning review, this has already been set up, but amplitudes in n=4 Yang-Mills theory are indexed by, first of all, certain integers. N labels the particle number, K labels the helicity sector, L labels the loop order, and then there's a purely mathy generalization that has no analog in physics, but the mathematicians like to introduce because then they can play various related games. There's this M parameter, which is always equal to 4 in physics and everywhere in my talk. So throughout the rest of my talk, any place you see a 4, it should be M, and any place you see a 3, it should be M-1. Okay.
Just a little question. Why n starts with 4? Is 3 particle motion?
Right. Yeah, I guess you could include 3 there, but it's so particular, it's so special, it's just you can write it down once and it's known exactly. Yeah. Yeah. Good. Yeah. I didn't want to put it there because then what would I have done here anyway? Yeah, the 3 particle amplitudes are special and they're exactly known and fully determined. So in addition to these discrete parameters, the amplitudes are non-trivial functions on a certain kinematic configuration space, which we can realize as a quotient of the Grassmannian. So I'll always be thinking about a representative being an n×4 matrix called Z. This is the momentum twister matrix modulo the action of GL4 acting on the right. Okay, so just to orient the rest of my talk with what we've seen already in previous talks today, tree level amplitudes, those with L=0, these are the canonical form on the Amplituhedron, which is conjectured to be a positive geometry. We've heard a lot about that from Thomas Lamb's talk, so he explained what the notion of canonical form is. So if you calculate the canonical form on the tree level Amplituhedron, that literally computes tree amplitudes. And as has been emphasized, this always gives you some rational function of the Plücker coordinates on this n×4 matrix. Yes.
It's just conjecture that the Amplituhedron is positive geometry. What does canonical form mean here?
Well, yeah, it's conjecture that it's a positive geometry and that its canonical form calculates the amplitude. In contrast, as Anastasia also mentioned, for loop amplitudes, there's another step that's necessary, and that's doing the integrals. So the loop Amplituhedron, which I'll review towards the end of my talk, gives you a rational form that we call the loop integrand. But then to actually get amplitudes, you have to integrate that object, so you get some form here. That you have to integrate over the configuration space of L lines in P3. And when you do that, you get a multi-valued function, you get these polylogarithmic functions, or even worse types of functions on the kinematic configuration space. So these two slides just emphasize the really important conceptual and mathematical distinction between tree amplitudes and loop amplitudes. Okay, but that's the end of my lightning review, since you saw most of that before. Okay, this you've also seen in the previous talk. Amplitudes are known or believed to be generalized polylogarithms if and only if the conditions here are satisfied. And I will only talk about these in my talk. So amplitudes outside the class of generalized polylogarithms are starting to become well studied in our community. The tools are starting to be developed for those, but the avatars of them in n=4 Yang-Mills theory are exceedingly complicated, and very little is known about them yet. So therefore, I need to restrict my attention to generalized polylogarithms. And as we heard in Anastasia's talk, the analytic structure of functions in this class are fully encapsulated in their symbol alphabets. Okay, so for n less than 6, the dependence on z is trivial. You only get constants or numbers. Now that you get interesting numbers, to be sure. There's interesting structures of zeta values and multi-zeta values in these amplitudes. That is of interest to some physicists and mathematicians, but that's not what I'll be focusing on in my talk. For n=6 and 7, we heard that the symbol alphabets are equal to the cluster variables on the Grassmannian cluster algebra GR4n, first observed some time ago, and supported by all evidence available to date. We heard about references to calculations up to 8 loop order by Dixon and Liu, and here's a link to the same review article we've already seen. All right, but the purpose of my talk is to focus on the new ingredients that emerge when n is greater than 7. Okay, and some of the new ingredients are that, well, the most important new ingredient is that the GR4, n cluster algebra becomes infinite when n is greater than 7. And that reflects additional complexity that we see in amplitudes as well. So let me review on the next few slides what we actually have seen in amplitudes calculations for n greater than 7. And this is kind of going to be a dynamic slide here. So the first calculations go back already to 2011. Caron calculated the 2-loop MHV amplitudes for all n. He calculated, and his calculations revealed that the symbol alphabet for the n particle amplitude had n/2 times n² minus 8 and minus 17 Plucker variables. So the P1, my pointer is, oh, there's my pointer. P sub k refers to homogeneous degree k polynomials in Plucker coordinates. So P1 just means Plucker coordinates. So he found that in the symbol of the endpoint amplitude, he found this many Plucker coordinates, which is, well, how many Plucker coordinates are there? Well, in GR4, n, there are n choose 4 Plucker variables. So this number is generically less than that number. They happen to equal each other for 6 and 7, but starting for 8 points, starting at n=8, this number is strictly less than that number. He also found certain quadratic polynomials in Plucker coordinates. In particular, he found precisely n times n minus 5 times n minus 6 of them, all of which, I'll get to your question in just a second, all of which are cluster variables. So the total number of symbol letters he found here are split in this way between Pluckers and quadratics, and they're all cluster variables. Yes.
Which number is less?
I think this number is less than this. This grows as n to the 4th for large n, and this grows as n cubed for large n.
Yeah.
So
why is it a problem?
No, it's not a problem. It's not, I'm just saying he found a subset of them. Yeah, for n equals and 6, for n equals 6 and 7, he found all of them. And for n greater than 7, he found a proper subset. And again, here, this is a proper subset because so the Grassmannian cluster algebra GR4 comma n is infinite when n is greater than 7. But for any finite degree in Plückers, there's only finitely many cluster variables. So for example, there are n plus 7 times n choose 7 quadratic cluster variables, and he found in his calculations a proper subset thereof. Okay, so it's already kind of interesting to ask, like, can you characterize what is there anything particularly interesting about that subset, or is it just kind of some kind of accident at having looked at a sufficiently simple amplitude that has an accidentally simple structure? So to get some insight into that, let's start looking at more complicated calculations. So He, Li, and Zhang have computed two-loop NMHV amplitudes for n equals 8 and 9 particles. Anastasia also referred to these. They found 68 or 117 Plücker coordinates, 96 or 333 quadratic cluster variables, and 16 or 81 cubic cluster variables. And here, just for reference, I list the total number of cluster variables of this type, whether Plücker, quadratic, or cubic, for the GR 4,8 and 4,9 cluster algebras. Okay, so this is all very intriguing. Still, you can wonder if there's a pattern to these cluster variables that are being found. Or you may wonder, well, maybe we don't have enough data yet to really understand what's going on. But there's something else that they found. They found that there are certain symbol letters that are not cluster variables. In fact, they're not even polynomials in Plücker variables. They're algebraic functions in Plücker variables. So I'm going to say a lot more about these in a few slides. So they found for n equals 8, they found 18 algebraic letters, and for n equals 9, they found 99 algebraic letters. And there's a big red X here because they're not cluster variables. They're closely related to the cluster algebra, as I'll say a little bit, and as I'm sure we'll hear from Danny later in the conference. But the big red X means they're not cluster variables. Okay, so, well, continuing along a semi-historical route, here I'm going to keep the leftmost column, but replace the rightmost column by subsequent calculation of the 3-loop MHV amplitude. And what we're finding here, so it's interesting, these numbers are now kind of directly comparable because both of them refer to n equals 8. Both of these refer, oh, in fact, I should have deleted this column here because it's now no longer relevant to this slide. Both of the columns here refer to n equals 8. So I should only be looking at the GR 4,8 numbers there on the right. So 68 Plücker coordinates, 104 quadratic, 32 cubic. And this table implies, but I should make it explicit, that this 96 is a proper subset of that 104. This 16 is a proper subset of those 32. So as you do more and more complicated calculations, you start to see more and more cluster variables, but this 18 was somehow stable. It's the same 18. Okay. Yeah, go ahead.
Well, because like,
yeah,
because this number are very close to 68, 70. Yeah. So it should be like 2 that with the coordinates.
Yes. Yeah, it's 1, 3, 5, 7 and 2, 4, 6, 8. And yeah, let me come back to that point. Yeah. And then the missing 9 here are exactly the analogous. Okay. Then then the next data point is a calculation of the 2-loop and squared MHV amplitude. And it's intriguing because these numbers are now starting to stabilize. Okay, you get 104 again, 32 again, you get the same 18 algebraic letters. But there was a new ingredient because they found here, I hope those of you in the back can see that I've added another row here. I've added a row for degree 2 polynomials and Pluckers that are not cluster variables. Okay, so the algebraic row, we already know they're not cluster variables because they're not polynomials, they're algebraic. But they found something new here in this amplitude, which is a couple of quadratic polynomials and Plucker coordinates that are not cluster variables. Okay.
Are those quadratic polynomials still positive on the positive part?
Yes, I'll get to that. Yes, exactly. That's a crucial hint, like a smoking gun or something. But I added the word stable here because it's tempting to wonder whether these numbers have now somehow stabilized and whether there's something special about these 18. I mean, okay, some of you in the audience know there are very special things about those 18, but I'm just saying, just from staring at this data, it makes you wonder about that question. Okay, so here, in order to highlight, in order to really focus in on these interesting ones down here in the rows that I've marked in yellow, let me introduce some quantities. So here's this quantity A. So this quantity A is quadratic, it's a homogeneous degree 2 polynomial in Plucker coordinates, and it's one of the two that are listed here in the table. The other one is the one you get by cycling by 1. Okay, and then I've defined a quantity B, and then I've defined a quantity delta. I'm sorry if that looks slightly like A, but that's meant to be delta, which is A squared minus 4B. And you can check that none of these are cluster variables of GR48. And the algebraic symbol letters, there are 18 of them. So they're kind of two copies of this whole story. There's this copy and the copy you can get by cycling everybody by 1. You see that if just by looking at this, if you cycle by 2, you come back where you started with. So there are two different orbits under the Z8 cyclic group. So in this universe, there are 9 algebraic letters, and all of them have the same discriminant. All of them have the same square root delta, but they have slightly different, the A here changes to various different, there's sort of 8 different A primes that can appear. If I were to list out the 9 different algebraic letters, I'd have 8 different A primes here. But the A is particularly special, which is why I've listed it separately there. The A is also special because it's the one that appears by itself as a symbol. Okay. Well, yeah, go ahead. Yeah.
So you just mentioned discriminant.
Well, okay. I mean, I just because you define something A and then you define something else B and you define something else to be A squared minus 4B, then you're sort of building in that it's supposed to look like a discriminant. But this delta is the thing that vanishes. So if you have 4 lines in P3 and then you can make 2 lines that intersect all of them, and this vanishes precisely when the 2 lines are
when is that true?
so it actually is a discriminant. Yeah. Good. Okay, but still notice that almost all this data is still restricted to relatively low loop order. It's mostly 2 loop data with one little addition of 3 loop data here. Contrast to the story we heard about in the previous talk, where data is available all the way up through 8 loop order. So there are some big questions that are that we really don't know the answer to. Yeah,
Okay, is it, if I recall, is that associated with the four mass box?
yeah, this is what we in physics call the four mass box discriminant. Yeah.
So you have a weakly separated collection. It's something
Yeah.
associated.
Yeah, that's right. So, big open question number one is, if we fix n, does the number of symbol letters grow without bound as L increases, or does it stabilize? So if I start doing 4, 5, 6, 7, 8 loop calculations, will this number grow to saturation? Will I start to see higher degree polynomials in Plücker coordinates? Or will it stabilize at some loop order? Suppose it goes on forever. Does the list of symbol letters eventually include all of the infinitely many cluster variables, or only a proper subset? We don't know the answer. Is that subset finite or infinite? And the most important question, the reason why we're bringing this to your attention, to the community of mathematicians, is that it's really interesting to know whether there's a natural mathematical characterization of this set. The set of cluster variables that we see, as well as the set of algebraic and non-cluster variable symbol letters we see. Because, as Anastasia mentioned, if we had some other mathematical problem which is explaining the pattern of what we're seeing here, then we could use that as a hypothesis that would allow us to bootstrap amplitudes, or at least make reasonable guesses for amplitudes that are currently beyond our ability to compute. And then, we have various ways of applying consistency conditions and checking whether hypotheses make sense. So it would be incredibly valuable to have any information on this.
Also,
Yeah.
concerning the first question, the set of Landau variables stabilizes actually for arbitrary loops. Isn't that true?
I think so, but you say that that's true, really?
I think, well, I checked something with some.
Okay. So exactly. So had you asked me a few years ago, I would have emphatically agreed with you. And I said, yes. And that's why we know that it has to stabilize. But then following our recent work that Anastasia described, where we found a loophole in that argument about the ziggurat graphs, that makes me doubt. Let's just say I don't, it should be more firmly understood, or at least explained to me. Yeah. Yes, Yara.
So did it say that despite some letters only show up in MPT, that there is some sort of certification that there is no
Well,
which is actually
I can repeat the question. Yeah, I can. So Yara's asking, do we expect some kind of stratification that will explain why some letters maybe only appear for MHV amplitudes, and then some larger set of letters appears for NMHV? Okay, I mean, the scientist in me says that sounds reasonable, but maybe we don't have enough information to be sure yet. But actually, I would guess that anything that's missing here is missing only for accidental reasons, and that if you fix and go high, what am I trying to say? I'm trying to say that Anastasia described the Q-bar equations, which tell you which relate higher loop amplitudes to lower loop amplitudes with higher n and k. So if you go to sufficiently high loop order, everything will have fed in. So I think you'll see, like, for example, if you go to sufficiently high loop order, even in the MHV sector, you'll inevitably see everything as complicated as can appear in NMHV sector and higher. So I think asymptotically there may be no stratification of that type. Okay, so there's one important clue we have. Lauren already made a comment about this. So a working hypothesis that is supported by all evidence available to date is that amplitudes have no singularities when you evaluate them for this momentum twister matrix Z being a positive matrix inside the positive Grassmannian. And just to be absolutely clear here, what I mean by singularities is no branch points. We know that there cannot be any poles. I mean, it's not trivial because every way that you write an amplitude, there will always be spurious poles, but we know they have to cancel out at the end. The non-trivial part of this statement that I'm trying to emphasize is no branch points. So if we look back again at these expressions that I was using a few moments ago, it is definitely not obvious. So there are two minus signs there. It's definitely not obvious that this quantity A is positive valued inside the positive Grassmannian, but you can check that indeed it is positive. And in fact, it's over positive. This is a phrase that we used in our paper with Thomas and Nima. It's over positive because there's something else here that's positive that is strictly between A and 0. And you can prove that A is always greater than 2 times square root B. And you can prove that that 2 is optimal. You cannot decrease it. If you try to decrease that 2, then you can violate that inequality. So
It's how the way come to the inputs.
I'm sorry.
Well, if you look at A, see that this is template even.
Okay, yeah. Yeah. So yeah, I'm sure. Yeah, I'm sure for those of you who know the correct technology and have seen this kind of formula before, you might have a way of understanding why that's why that's positive. Yeah, that's exactly right. So anyway, consequently, the quantity A squared minus 4B, which is what I've been calling delta, that is positive inside the positive Grassmannian, so that you never run into any branch cuts of this square root. So, you know, it's all a consistent story that's falling together in our lap here. We have these things that are not cluster variables. We have these things that are algebraic functions but they're not arbitrary or algebraic functions. There's some very special, highly constrained structure here that's, you know, it's not the Wild West. There's clearly something quite beautiful, important going on. That's lying behind all of this. I think Danny will talk about some of the connection between some of these things and limit rays inside the GR48 cluster algebra. I want to briefly mention another connection, which is that the 18 algebraic, okay, actually, let me take a step back. There are various ways to derive or associate 18 algebraic letters to the GR48 cluster algebra, which is an infinite cluster algebra. And they have to do with infinite mutation sequences and taking some kind of limits inside the cluster algebra. Now, that's wonderful and beautiful, but also so GR48 is kind of two-faced. If you look at it one way, it's an infinite cluster algebra, but if you like squint and look at it sideways, in some respects it behaves like a finite cluster algebra because it has finite mutation type. So, but even though it's finite mutation type, it has an infinite cluster automorphism group. So when we say that there are limiting rays, there are infinite sequences and mutations that can take you off to infinity, and you can look at infinite sequences along those. If you're in the full GR48 cluster algebra, there are actually infinitely many of those, because for any one of them, you can do a braid group transformation. The braid group is a subgroup of the cluster automorphism group for GR48, and so you can get infinitely many different infinite rays in GR48. Okay, what was the point of this long digression? The point was, suppose it really is the case, we don't know if this is true, but suppose it were the case that you can compute up to arbitrarily high loop order, and you will still only ever get these 18 algebraic functions. Never anything more complicated like an image of one of these under a braid transformation. Suppose it was literally just this finite number 18. There are various games you can play to get finite things out of GR48. I mentioned a couple, like modding out by cluster or Morrison group or whatever, but this is all this one big long segue into part 3 of my talk. There's a very natural way in which these 18 algebraic letters appear in something that's related to the Amplituhedron. So actually, it was really spectacular because during the course of this work, we realized many years after the fact that these 18 algebraic letters were already there in the book, in Yaroslav's book on the positive Grassmannian. So how that works is as follows. As we'll hear more this week, our friends Evan Zohar, Leclerc, Parisi Sherman Bennett, Tesler Williams define a tile to be the image of a cell of the positive Grassmannian under the Amplituhedron map, which is defined by multiplication by the matrix Z. Provided a couple of additional criteria are satisfied. Number 1, they demand that the Amplituhedron map be injective, and number 2, that the image be 4K dimensional. And in such cases, assuming that these tiles are positive geometries, the canonical form on the tile is what in physics we have long called a Yangian invariant. But in physics, we use that term even for a broader class of objects where you can relax some of these assumptions. And sort of the most innocent one that you could relax among these assumptions is the requirement, the most innocent one you can relax is this requirement that the Amplituhedron map should be injective. And an example of what you get when you relax that requirement can be seen by looking at this Plavik graph, which describes an 8-dimensional cell of the totally non-negative Grassmannian 2, 8, on which the Amplituhedron map is not injective, but 2 to 1. Okay? So this is an example for the n equals 8, m equals 4, k equals 2 tree-level Amplituhedron, on which you get a cell where the Amplituhedron map is 2 to 1. So then I allow myself to use the word tile in quotes, meaning it doesn't satisfy the technical definition of tile that I just gave on the previous slide, but it's kind of the generalized tile in the obvious way. And its facets, I'm glad that Thomas gave these beautiful lectures because I can freely talk about facets being cut out by equations in the Grassmannian or whatever. The corresponding tile has facets that are characterized by algebraic equations. So equations that are algebraic in the Plücker coordinates and that involve precisely 9 of the 18 algebraic letters. The other 9 are given by taking this I didn't write the external labels, which is a shame because they're important. There are 2 copies of this graph depending on whether you do 1, 2, 3, 4, 5, 6, 7, 8, or 2, 3, 4, 5, 6, 7, 8, 1. So those 2 copies precisely sort of give you a story explaining those 18 algebraic letters. So to make a long story short, if it turns out that one day we prove or discover that to any loop order, 8-point amplitudes in Super-Yang-Mills theory only have these 18 algebraic letters, then we will understand they were staring us in the face the whole time. They're precisely the 18 algebraic quantities that appear very naturally from this construction. Logically, it could happen that when we start computing the 87 loop amplitude, we start encountering more complicated algebraic quantities, algebraic letters that perhaps are grade group transformations of these 18, or perhaps there's something even more complicated entirely. So to take a step back, let me remind you, we're just trying to find some other kind of mathematical game whose solution describes the same pattern or the same structures that we're seeing in amplitudes. But regardless, it would be very interesting to consider, study such tiles in quotes further. All right. So I have a few minutes left. I want to mention something about an important concept called cluster adjacency, because amplitude calculations have revealed much more structure than just sets of symbol letters. Everything I've been talking about so far is just trying to describe sets of symbol letters for a fixed n. And one of those structures is what we call cluster adjacency, and this has three manifestations. One is that for loop level amplitudes, this is the context in which it was first discovered by Drummond, Foster, and Gerdegan. Two cluster variables, x and y, can appear next to each other somewhere in the symbol of an amplitude. So these symbols, they're linear combinations of many terms, and in each additive term has the structure of a tensor product, and this is ordered. There's definitely an ordering here from first to last. Two cluster variables can appear next to each other in the symbol of an amplitude only if they're compatible. And this is compatible in the mathematical sense. Two cluster variables are compatible if there is a cluster that contains both of them. Correspondingly, if two cluster variables are not compatible, you'll never see them sitting next to each other in the symbol of any amplitude. This is what we call loop level cluster adjacency. There's also a tree level version of this, which is that if you look at the poles in any Yangian invariant, they will always be jointly compatible. That means there will be a cluster that contains all of them. So this was originally phrased in this way in terms of poles of Yangian invariants, but working backwards through this set of definitions where poles of Yangian invariants are associated to facets of the corresponding tile, I think it's fair to say that this was proven in a morally equivalent form, that the facets of any Amplituhedron tile are jointly compatible cluster variables, and we'll also hear more about that. There's also a hybrid version of cluster adjacency, which says that when you have loop level non-MHV amplitudes, these can be written as linear combinations of transcendental functions times Yangian invariants. And the statement here is that the final entry in each term of the symbol is compatible with all of the cluster variables in the denominator of the Yangian invariant that term multiplies. Okay, I haven't paused to ask for questions, but are there any questions? I'm going to move on to the next topic. All right. So section 5 was meant to connect to the Amplituhedron because the Amplituhedron is in the title of this conference. And many years ago, starting almost 10 years ago, actually I put the references at the end, I don't know why, we initiated a program for trying to derive symbol alphabets for scattering amplitudes in n=4 Yang-Mills theory from the Amplituhedron. And I want to give you a cartoon for how this goes. Anastasia already set up the bulk of the machinery I'll need because it's based on the Landau equations. But let me give you a cartoon of how this story goes. So first of all, let's recall the definition of the loop level Amplituhedron that Yara did mention in his talk. So given external data, these are the momentum twisters. The loop level Amplituhedron, and just to make things very easy, I'm going to focus here on the MHV Amplituhedron, so K = 0. Normally that's kind of, I mean, at tree level that's trivial, people don't usually bother talking about it, but at loop level it's definitely non-trivial. And the loop level amplituhedron, I mean, you can generalize this to non-zero K, it's just notationally more cumbersome and I didn't want to spend too much time on it. But the loop level MHV amplitude is the space of configurations of L lines in P3, all of which can be written, the whole, this is awkward, the definition didn't quite fit on one slide. Okay, this is awkward. So we're gonna have to remember this and go to the next slide. So, okay, we have our external momentum twister matrix, which is an n×4 matrix Z. And then each of these capital Ds is a 2×n matrix where, so each line here, each of these curly L's is a line in P3, which I'm understanding is being represented by an element of GR2, 4. So these are 2×4 matrices on the left, and on the right we have 2×n times n×4. Okay, now, such that all ordered maximal minors of all of these collections of matrices have to be positive. Okay. This is the definition of the loop level MHV amplituhedron. A key consequence of this definition is that inside the amplituhedron, all of these inequalities are satisfied. That the bracket of any one of these loops, you know, again, I use the word loop and line interchangeably because it's a line in P3. But it corresponds, when we think about Feynman diagrams, it corresponds to a loop in the diagram. And again, I think of any line in P3 as being represented by 2 points that it passes through. So given a line, I can calculate the 4 bracket of that line with 2 other points by just smashing them together and taking the determinant. And so here, this bracket is shorthand for the 4 bracket L sub L Zi plus 1. Anyway, a consequence of the definition is that all of these brackets have to be positive inside the loop amplituhedron. Okay. Oh, this I don't need to say because I already said, oh, but I need to review it. Yeah. The amplituhedron is conjecturally a positive geometry. So there exists a unique canonical 4L form with logarithmic singularities on the boundaries. And as I said at the very beginning of my talk, loop amplitudes are integrals or periods of this form over some particular contour dictated by physics, mysterious, but in principle dictated by physics, in the space of all loop momenta, i.e. in the configuration space of L lines. So to get a flavor of what's going on here, let's look at some possible singularities that could emerge as we're calculating this integral. Well, we consider the rows of the external data matrix as the homogeneous coordinates of n-ordered points in P3, that we know. So we have these n points in P3, and we draw a polygon that connects, each one to its neighbors. And as we've heard, the positivity of this matrix is a generalization of the notion of convexity to higher dimensions, so I'll always draw it as a convex polygon, even though it lives in higher dimensions. Each one is a point in P3. Okay, then a positive loop momentum, meaning one that satisfies the definition for it to be in the loop amplituhedron, is a line that threads through this polygon, as I attempted to draw there. And if you have more than one loop, if L is greater than 1, then you have a collection of lines that have to satisfy some kind of mutual positivity conditions. So each one has to pass through the polygon, but there's also a mutual positivity condition that enforces constraints on their relative orientations. We heard about this in Yara's talk in the special case of 4 particles, where it's particularly simple. Now imagine what happens as we do this integral. So we integrate over the space, the configuration space of lines. Naturally, we'll encounter poles in that integral when the line, for example, hits one of the edges here of the polygon. Let's say it hits on the line segment between Zi and Zi plus 1. So it will get the integrand will develop or the integrand, AKA the canonical form on this geometry, has a pole when this is satisfied. But this pole in the integrand doesn't need to lead to a singularity of the amplitude because we can deform the contour of integration. Singularities of the integrated amplitude are forced to occur when poles collide so that you can't deform the contour. The contour is pinched. At one loop, there are two basic types of such pinchings. So these are both codimension 2 boundaries. Either you can have reach a codimension 2 boundary of the loop amplituhedron where your line actually passes through one of the points. That means that both of these conditions are satisfied. Or you can have that the line passes through two segments of your polygon, which could be adjacent or far apart. And then these two conditions are satisfied. Now, let's say we want to determine what is the location, so these singularities won't be realized generically for generic Z. We need to determine what are the constraints on the Z that allow these to be attained, because only when the Z satisfy those properties will this actually be a singularity of the integrated amplitude. So to answer that question, what we had in mind was to approximate the canonical form, which in general is some complicated object. We imagine approximating it in a neighborhood of the singularity we're looking at by a single Feynman diagram with the same pole structure. The basic idea is that we know that in principle you can calculate this canonical form by summing up Feynman diagrams. I mean, it's maybe the worst way in the world to compute it, but at least as a proof of principle, that is a valid method. And in the neighborhood of these singular configurations we're looking at, we can approximate it by replacing it with the single Feynman diagram with the same pole structure. That's the 0th order approximation in these singular neighborhoods. So the top line we would replace by a Feynman diagram that looks like that. It's a bubble diagram. Well, both of these are bubble diagrams in this case. Then we can use the Landau equations, which say, Anastasia reviewed, they say that a necessary condition for a Feynman integral of a certain topology to have a singularity is that where you have some external and internal momenta. The necessary conditions to have a singularity is that these equations admit a solution. So we can use that criterion to associate to each one of these boundary configurations of the amplituhedron, we can associate a condition on the Z matrix such that the associated singularity is realized. So for example, this singularity on the top row is realizable when I plus 1, jj plus 1 is equal to 0. And the one on the bottom row is realizable either when ij minus 1 jj plus 1 is equal to 0, or I minus 1 I plus 1 j is equal to 0. Okay, so in this manner, you can sort of read off the possible symbol letters of an amplitude directly from these kinds of boundary configurations in the amplituhedron. And I should emphasize, I think I didn't emphasize what the point was, that there was a question about it at the end of the previous talk. If you look at the Landau diagrams of a single Feynman diagram, you may find a lot of spurious singularities that cancel out when you add up all Feynman diagrams to get an entire amplitude. However, the amplituhedron is supposed to tell us which ones of those are spurious and which ones of them are non-spurious, because the spurious ones correspond to fake boundaries, some random locations in the middle of the amplituhedron, and the real ones, the honest ones, correspond to boundaries of the amplituhedron itself. So by tying the
Landau analysis to the amplituhedron geometry, we can effectuate this map. Now, I'm running out of time here and I didn't want to go into too much detail. In principle, I know of no conceptual obstruction to determining the singularity structure or symbol alphabets from the loop amplituhedron and Landau analysis along the way that we outlined in these papers several years ago. However, at the time, our technical ability to actually solve the Landau equations was rather limited. And also there are a number of subtleties having to do with infrared divergences that we, well, to be honest, we maybe wouldn't have known how to do properly if we didn't know what was the correct answer that we were supposed to be getting. However, in recent years, there's been tremendous progress in understanding how to solve Landau equations and analyze them properly, dealing with infrared singularities and taking care of everything properly and doing all the right blowups. So I think the time is definitely ripe to revisit some of this analysis for more complicated boundaries of the loop amplituhedron. Okay, so in conclusion, the scattering amplitudes of n equals 4 super 8 Mills are a remarkable collection of functions with rich mathematical properties. Indeed, we often say that they barely exist in light of all the physical properties that they have to satisfy and the mathematical properties that they evidently have, and that this is an invitation for the mathematicians in particular to really start taking a look at the loop amplitudes, which remain largely unexplored and have a lot of structure still to be discovered. Thank you.